Hello and welcome to a demo of the Reservoir Modeler for Abaqus. The Reservoir Model is a plugin, so I'm going to run on down under here under Plugins and initialize it. So we see over to the left here we have a Reservoir Modeler tab. We've got some icons up front, User's Manual, example manuals, and then a couple of icons for translating from a Geomechanics model to an Abaqus output database. So typically what we would do is we would, for example, with Eclipse, we would have a bunch of files that are Eclipse files. We'd add some options, and basically what this does is it runs in a method called from reservoir, and it converts all of the Eclipse data into an output database file that Abaqus can read, and then we can import it into Abaqus CAE and work with it. So what I'm going to do is we'll go through this process, assuming that we've already got that translation process completed. So the first thing I'm going to do is create some horizons. And this would be, some type of seismic data that you might have that would define layers of rock. What I'm going to use those for later is generating the burdens. So the first step here, we're going to go off and create a reservoir. I'll use a default name. Now I've already got an output database that was created from the translator. I'll just hit OK. And we've initialized a reservoir. So this is our reservoir that was generated from an output database, well, from the Eclipse model, which is now an output database file. So it just has the reservoir information. So if we look at it, for example, layer 1 has been broken up into things like the active regions, the elements that have just gas in it, and that might be broken down into subregions, and then elements that have no gas, oil, or water, and the elements with oil and water and so on. So the first step in this process is about a 10-11 step process, and it's sequential. We've got to go through here in order to create a model inside of Abaqus, get it run ready, do all the initial geostatic analysis to ensure that everything's in equilibrium. We have to run through about these 11 or 12 steps. So the first one we're going to do is just perform reordering, and there's no options to that. It's just a step we have to perform. And what that does is it changes the element number in such a way that later on when we merge, let's say 2 layers, the layer with the larger volume of fluid will retain that element number, and basically what we'll do is we'll retain some of its properties like fluid, the amount of fluid and things like that. All right, so upscaling, that's where we have meshes, for example, in this case, where we have this element that collapses down into a wedge. Now there's actually 2 nodes here, so if we were to try to create a burden and extrude this face out, we would have a brick element that's basically collapsed down, and the solvers would fail with an error. So what we have to do is merge those layers into one. So this is the only step in this process that we're going to have to jump out of the plugin and work within the Abaqus CAE. Alright, so I'm going to choose to merge layers. It says select elements instead of individually. I'm going to select by typology. That way all I have to do is select an edge, and it'll automatically select the entire layer of elements. And then select element edge to indicate merge direction. Alright, so now we've merged the second and third layer. So what I'm going to do is double click on that, and all I'm going to do is just select these 2 and say I've merged them. Now this step is not actually necessary. It's just for bookkeeping more than anything. As we'll see as we go through some of the other steps, we'll reference the original layer number and the merge layer number. It'll just kind of help us keep things straight. Alright, the next step is we have to tell the plugin which are the surfaces, top, bottom, left, right. First of all, the Z direction is always going to be in the global Z direction. So the plane of the reservoir is always in the XY direction, but it can be rotated. So we're going to assume that it's the X direction of the reservoir is in the global X direction. So we're just going to need to pick some faces. So I'm going to pick the right face. Positive X direction would be this one. Negative Y would be that one. Top. We'll rotate this around. Negative X be here. And finally the bottom. Alright, so all that's really done is just generate, if we look at the surfaces, all that step is really done is create some surfaces with an Abaqus CAE. Alright, so the next step is actually creating the burdens themselves. So the first information up here is just some summary of the reservoir. It gives the minimum and maximum coordinates in the X, Y, and Z direction. So it gives you some idea of how big it is, and that'll guide you in creating the burdens. So what I'm going to do is the top burden, I'm going to do it by horizon table. I'm going to add these horizons. Alright, so it tells me the maximum Z coordinate as far as the depth, or max Z coordinate. So the number of elements, we'll say, we're going to keep a very rough mesh here. Element bias just means the first element, in this case, would be half of the size of the second element. And by burden, I'll do it by global X coordinate. So we see our minimum Z coordinate is negative 2600 in the reservoir, so we'll make the bottom negative 5000. Side burdens we'll do by X coordinate. Basically, I'm going to add and subtract 5,000 to all the sides. Then if we want to change, let's say, the number of elements in the burden areas, we can do that. Change the bias. Okay, so let's clean this display up a bit. Just we'll hide the datums. All right. So the next step is we're going to go on and assign material properties to the burdens. Now this step doesn't assign the properties to the reservoir, just the burdens. So the burdens are not porous elastic, they're just purely elastic. So I'm just going to set every layer to the same value just to make life a little bit easier for us. Okay. So we see the top layers that were generated by the top burden, and then the layers of the reservoir. Now these are the burdens on the sides of the layers of the reservoir, and then finally the bottom burdens. Alright, so the next step we're going to do is walking through the process. We are going to set up densities. Now the densities can be, we can make them a constant value throughout, or what we can do is enter an expression. So I'll just kind of clean that up and say from negative 3500 to 0, we'll just say a constant value of 1200. Then I'm going to add a row below. So from 0 to a depth of 5,000, you know, we could put anything we want here, but I'll put an expression 0, 1, some kind of expression like that. Alright, so we can put it layer by layer and have some mathematical function of how the density varies. Alright, so with that done, the next step is to provide the elastic properties of the actual reservoir region itself. So again, I'm just going to set all of them to the same value. And then the inactive regions, well, the inactive regions don't have any fluid, so instead of elastic properties, we'll just enter, or instead of the porous elastic properties, we'll just enter the elastic properties directly. Okay, so at this point, we've actually got all the materials assigned to the region. We've got the burdens created. Now we just go through the last few steps of setting up the model. So the first step is how are we going to define the pore pressures? Well, we read directly from the original ODB, and the same with the initial void ratios. So the first two values here are read by the plugin, so it recognizes that the top vertical coordinate and the bottom vertical coordinate are here. So what are the stresses in the elements with fluid and the elements without? So, and these are just approximate stresses. So it's basically an initial guess at the stress, and then the solvers will run through, use those initial stresses, and then iterate until it finds a solution that is in equilibrium. Okay. Now, if we wanted to, we could put a pressure load. Let's say this thing was underwater. We could put a pressure load based on water depth and density of the water. And we'll skip that step. Alright, so at this point we have a run-ready model. Now typically your models would be much bigger than what we have here, so you could use this, hit OK, and it'll generate a Python script. Then you could move all your files that you need over to, let's say, some cluster, or even work on your current desk and run a script to actually run the models. Now we can't actually generate a job within Abaqus CAE because some of the commands that are required on the command line to run it are not available, not supported in Abaqus CAE. So again, we could use a script to do that, or since this is a small model, I'm just going to do it interactively. Now we have one last option here, and that's this geostatic iterations. And what that does is, if we choose to, we can set the lateral stresses to some fraction of the vertical stress. And what that'll do is it'll allow the solvers to first run through with our initial guess at the stresses, and then run a second time where it actually reads the stresses and sets the vertical stresses directly as a function of or sets the lateral stresses as a function of the vertical stresses, sets that as the initial stresses, runs it again, and then you could do that a couple of iterations to get closer and closer to equilibrium and get those numbers closer and closer to these values. So we'll skip that. That slows us down a little bit. So we'll just submit the job interactively. So what it's doing now is it's running the geostatic analysis with purely elastic properties and finding a solution to the stresses throughout the model. Now we know that the rock goes through plasticity, and we're going to model it with clay plasticity, but we're doing this, so far this whole process has just been just used in order to get an initial estimate at the stresses. And then we'll use those as initial stresses and use those stresses also to calculate some plasticity coefficients to be used in our clay plasticity. Okay, so the job's completed. Now we'll go to the next step, and all this does is we're just going to read the ODB in, and the plugin's going to read the stresses and store those for the next step. Okay, so now that the analysis is completed and we've read in the stresses, so what that last step did is it just computed the effective vertical stresses for all these different regions, the effective void ratio. So now we just need to fill out this table of different parameters for the clay plasticity model. So again, I'm going to set them all to the same thing. Okay, and then the inactive regions, same thing. And finally the burden region, same thing. Okay, we'll submit it. Now it'll actually calculate all the material properties and update all the material definitions. Now if we'd like, we can review those properties, and here's all the properties that were computed based on the stress distribution and those parameters that we'd given. So now if you'd like, what you could do is, let's say these areas here, I'm going to say enable override of modulus. So let's say some of these we have a better idea of what we think they should be. So we could say 0.0008. So if we want, we can override individual quantities. Otherwise, we can just accept what the plugin had calculated. Okay, and then we go through our final step just to verify. Alright, now the final analysis is done, so let's actually open up the results. And let's say contour the stresses. So we see a fairly uniform distribution vertically. Now let's look at, let's say, the displacements. And we see a very small set of displacements, 1e to the negative 6. So when you're talking meters, you're talking, you know, 1/10 of a millimeter, something like that, or 1/100th of a millimeter. So that's what we want. We wanted to see that this thing is in equilibrium. We don't see a lot of deformation because presumably this data is exactly in equilibrium. And then from here we have the model ready to run, and we can then set up within Abaqus CAE, we can set up an analysis to read from the output database. We could read histories of pore pressures and things like that to calculate a subsidence history. So anyway, so this has been just a quick demo of the Reservoir Modeler. So if you have any questions, please contact us at the SIMULIA South office. Thank you.